Congratulations to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. In this episode, we're going to be diving into a couple of the different software architectural methodologies when it comes to building and designing your software, specifically monolithic versus microservices. Now, of course, microservices are the new kid on the block. It's what all the cool hip kids are doing these days with their AWS Lambda functions. But in this episode, we're going to just go through what each one is, break down the pros and cons, and just kind of do a comparison to hopefully give you a better understanding of each of them and potentially try to help you identify which one might be best for your next project. But before we get into that, let's start off with our trivia question for the week. This week's trivia question is the CUDA API, which is the way one would write code in order to run on an NVIDIA GPU, was released in what year? So what year was the CUDA API released? And that is your trivia question for the week. And speaking of NVIDIA has been in the news recently. No, not because its stock price has been going to the moon, but because it has really started to crack down on translators, is what it's calling it. So kind of recapping CUDA, as we kind of touched on in the trivia question, CUDA basically allows you to do high-performance computing, a lot of number crunching, AI and machine learning, and a bunch of different things directly on the GPU. Now, I've done a little bit of CUDA programming myself. I wrote a program to find the prime factors of a number. So as we've talked about before in terms of in cryptography with like public key encryption, one of the leading ways to do that, like with RSA, for instance, there's of course other ways to do this, but RSA uses this idea of factoring two very large prime numbers, basically multiplying them together to generate a key. So basically the point of this factorization program was to take the product of prime numbers as input and basically find what two primes were multiplied together in order to generate that value. So I did a comparison, one doing the calculation on the CPU versus one on the GPU. And yeah, the GPU kicks butt. I mean, it's the CPU, when you get to large numbers, it like takes a while to run, and then the GPU is just instant and does it all like right away. It's pretty spectacular. But anyway, that's basically kind of what CUDA is. It's a high performance language that allows you to write code to be executed on an NVIDIA GPU. Now, because CUDA is so good, people have developed translators to basically allow you to run CUDA programs on non-NVIDIA GPUs. And NVIDIA isn't exactly too happy about this. And now they are banning the use of these translators, which before they had them banned in their EULA, or their end user license agreement. But now they're also including them in the install files according to Tom's Hardware, which I'll have the link to this article down in the show notes below. But yeah, so basically people created things like Rosetta 2, like Apple created. So if you don't remember, Rosetta 2 was the solution that Apple created in order to allow you to run Intel-based programs or x86 programs on Apple Silicon or on ARM based systems. So basically what it would do was it would translate the x86 assembly code into ARM assembly code to allow the program to run on the system. So basically that's kind of what these translators are doing. In essence, they're translating the code in order to run that would natively run on CUDA in order to run on other types of GPUs like AMD and Intel, for instance. So one of these programs is called Zluda. I think that's how it's pronounced, Zluda. So Zluda is described as a drop-in replacement for CUDA on Intel GPUs. So essentially what this means is it allows you to directly run CUDA compiled programs on an Intel GPU. So basically think of that Rosetta 2 comparison, except in this case, CUDA is the x86 Intel, and Intel is the ARM assembly, or the ARM or the Apple Silicon. So according to the creator, he claims that it provides near native performance. Now, I would assume, just kind of like Rosetta 2 and any type of translation layer, you're going to have some overhead, because obviously you're going to have to translate the instructions. You're obviously not running them natively. So you are definitely going to be accruing some sort of overhead. Now, how much of that overhead you actually accrue is, I guess, up for debate, depending on the translation layer, how optimized the program. There's a lot of factors that go into it, but there is a chance that you, in theory, could see pretty good performance, but probably not as good as if you compiled it natively. So, like, that's one thing that we saw, when Apple transitioned to Apple Silicon. Programs that ran through Rosetta generally ran pretty well, but then when the native Apple Silicon version came out, they of course ran a heck of a lot better because they were compiled natively. So the translation does accrue some overhead, but there is also potentially a chance that you could see better performance running through the translator version than a native version, depending on what kind of hardware you're dealing with. So if you have a lower end GPU, like CUDA GPU or NVIDIA GPU, there is a potential chance that your CUDA program could run slower on that GPU than, say, if you had a super high-end like AMD or Intel Arc GPU or something like that. So there is potential that translated versions can be faster, but it also kind of depends on what kind of hardware you're running on. So anyway, I guess one of the differences here, though, is NVIDIA is specifically cracking down on the translator portion. So you take a CUDA program and then you run it through a translator to execute it on some non-NVIDIA GPU. But that's different than if you took a CUDA program and then essentially rewrote it or recompiled it to natively run on an Intel GPU or an AMD GPU. That's, of course, obviously completely fine. So, but NVIDIA just, I guess, doesn't want you using translation layers. Something, between like NVIDIA and Nintendo and all these other, companies that are like cracking down on like what users do with their stuff is quite interesting. We're seeing this kind of transition. Now, I guess obviously, I'm not a lawyer, but if you created a translator and you were able to, part of me kind of wants to think that you'd be able to do that, just because if you manage to write a program that can take instructions from one architecture and translate them into the other, I don't know how that would necessarily infringe on any kind of like copyright or trademarks or anything per se. Of course, I'm not a lawyer, so I don't know. But it's like the thing with emulation, where if you can reverse engineer the architecture and reverse engineer how the thing works, you're essentially immune from any kind of copyright things, because if you redid it yourself, it's not like you stole like trade secrets or anything, but it's a really weird situation. I'll have the link for the Tom's Hardware article down in the show notes if you care to do any more reading on that. And with that, let's move into this week's cybersecurity tip. Now, this week's cybersecurity tip kind of goes back to the importance of physical security mattering just as much as cybersecurity. So this tip in particular is referring to when you go on vacation. So I know we're getting into the March season. It's March now. People are on spring break. I know there are some of my coworkers, I guess the kids in the county that I'm in, I guess this coming week is their spring break or something. So people are, taking off and whatnot. So the thing with vacations is one thing you have to be careful of, which is kind of the point of the tip, is not to, before you go, don't be like overly specific about when you're going to be leaving your house and when you're coming back, as well as where you're going. Because, and especially if you're one of the social media people, you're not posting pictures of your trip while you're still on the trip. And the reason for that is you're basically broadcasting to the world that, hey, I'm not home right now. Please come to my house and steal my stuff. Now, that's obviously not what you're saying, but to someone that wants to steal other people's stuff, that's basically what you're telling them. And as we've talked about before, physical security is one of the pillars of cybersecurity, and you could have the best cybersecurity in the world. You could have the most top-notch firewall and network security. You could have your devices hardened to the teeth. But if someone can actually break in and get physical access to your system, well, all those things that you put in place, all those cybersecurity measures are kind of a moot point. So yeah, physical security is definitely one of the pillars of cybersecurity, and it's not even that someone could get in, break into your house, and install ransomware into your home lab or something. That's probably not going to happen, but what would be more likely to happen is someone could break into your house, see all of your juicy electronics that they might be able to sell on some marketplace, or potentially try to harvest the data from if you didn't encrypt the drives. So lots of potential for bad things there. And of course, if they would manage to get hold of your personal devices, that could potentially have personal information about you, which then they could do some kind of identity theft, and yeah, lots of not so good stuff. So another way to ensure that your physical security is better than what it was. Be careful about when you go on vacations, what information you're giving out, and definitely don't be, posting about your vacation while you are still on vacation. So that is your cybersecurity tip for the week. Now, because we have a lot to talk about with software architectures, I think we should probably just move right on into what nerdy stuff have I been up to this week? Or I guess at this point, we almost should just start calling this nerdy things segment the weekly scrum. Because that's basically what it's turned into the past few weeks. I mean, if we're being completely honest with ourselves, how much of the nerdy things segment in the past few weeks has been almost exclusively me talking about software updates I've been making to the video game I'm working on? I would say the vast majority of it. I sprinkled in some home lab stuff here and there, but it's been mostly strictly software development updates. That's kind of basically what a Scrum meeting is you're basically going over, what you did, what you're planning on doing, and that kind of a thing. Except I guess the difference is generally Scrums are like a daily thing, and you kind of go over what you did the day before and what you're planning on doing for the upcoming week. Whereas in this, I basically just say what I did in the previous week and don't really say what I'm going to be doing, largely because some of the times I don't know what I'm going to be doing. And also because this is a complete side project, it's something I do in my free time. Some weeks I'll have more free time than others and be able to accomplish more than other weeks. Like, for instance, some weeks I might be able to get a few hours of coding in on my video game throughout the week, and other times I will be lucky to even open up the project at all. So that's one of the reasons why I don't kind of say what I'm going to do, but also there are some instances where I quite honestly don't know what I'm going to be working on until I sit down, stare at the code for a while, or just kind of go about my day and realize something that I could implement and go about doing that, which, to be honest, is probably not the best strategy, because one thing I've noticed specifically in the past few weeks is I have pretty much have set aside something that I know I'm going to be working on. So for a while there, it was working on the battle scene and integrating the back end and the front end GUI, and having, the mindset of when you sit down at your computer to work on development of either a personal project, a video game, or whatever you're programming, if you go into your development session knowing what you're going to work on, I've found, at least for me anyway, being a lot more productive and more consistent, because if I know what I'm going to work on or need to work on, I can basically get into the mindset right away and start, hammering out some code, rather than, sitting there for 30 minutes or 20 minutes or however long it is, looking through the code, trying to figure out what I want to work on. Because that is honestly one thing that I noticed when I wasn't essentially hammering out updates every week. Although in fairness, I had other not so fun matters I had to attend to, which we of course celebrated in December, if you'll recall that. So that's no more. So I definitely have a lot more free time now. But even before that, when I did have large chunks of free time, I didn't necessarily have a good idea of what specific feature I wanted to work on in my game, which is kind of why it just never happened, because I don't know what I'm going to do, so I'll just do something else instead. So I guess that's a off the wall, off the dome, tip right there. If you're trying to work on a side project or something, having not necessarily, scheduling out everything you're going to work on, but just kind of having the general idea of a feature or a milestone that you want to work towards, that can definitely help jumpstart you getting into your development sessions. Anyway, getting back on topic here, I went to war against Clang. And this isn't the first time I've gone to war against Clang, but it's the first time I went to war against Clang for this project in particular. And if you're not familiar, there's this thing called Clang format, which is basically a tool that will auto format your code for you, which is honestly pretty convenient, especially if you have a large code base or if you have a lot of developers working on a single code base. But the cool thing about Clang format is it has a bunch of pre-built styles into it. So for instance, you can select between Google's style guide, Microsoft style guide, GNU style guide, WebKit style guide, and there's a bunch of them. And you can basically pick which one you want, and it will automatically format your code to fit that style guide. So the one really nice thing about it is if you have, like I said, if you have a large code base, it can be easy to just format everything at once. I wrote a simple bash script that'll basically list out all the source files, pipe that in through Clang format, and format everything for me. The other thing you can also do is you can also integrate it with Git. So before you do a commit, you can essentially do a Git Clang format, and that'll automatically pipe all the files that you have staged to be committed to run through the Clang format and be, essentially auto-formatted for you. But the other nice thing about it too is you're not limited to the pre-made configurations. Like, you're not limited to just using Google, Microsoft, GNUs, or any of the other style guides. You can dump the configs of those style guides into a .clang format file, and then you can manually modify the contents of that file in order to more suit your personal style or whatever style you're trying to code in. So what I was basically doing the past week was fighting with the Clang format to try to identify which style best worked for me and how I could get the Clang format to format my code in the style that I wanted it to. Since, if I'm being honest, I didn't really care for any of them. And I say that I guess I'll walk that back in the sense that I didn't care for any of them in their entirety. So I liked bits and pieces of each one. Like, for instance, maybe I liked how Microsoft did curly braces, but how it did its formatting of casts. So if you were trying to cast, a size T to an integer, I didn't necessarily like how it formatted that. But on the other hand, I liked how the LLVM style formatted those casts, but I didn't like how they did curly braces or how they did spaces or, whatever the case may be. There were bits and pieces of each one that I liked and other parts I didn't. And I was basically trying to find the components of each one that I liked and basically make a hybrid that best suits my style. And one of the, I guess, potential issues is, and why I kind of wanted to go down this Clang format path, is at this point, I was looking at how many lines of code I've written, and we are over the 16,000 line mark, and trying to go back and manage all of those lines of code, some of which were written over 2 years ago, is quite the beast of a task. So being able to essentially run everything through Clang format and auto-format it for me was definitely something really appealing. Now, on the topic of code formatting is kind of a holy war when it comes to how heated people can get about stuff. So, for instance, tabs versus spaces is a fairly heated debate, although you should never use tabs and you should always use spaces because, first off, any good editor can auto translate your tab character into spaces, so there's basically no excuse there. But the main reason why you should never use tabs is because depending on the editor or the operating system you're using, tabs can be displayed differently, like I said, depending on what you're using. So in layman's terms, what that means is if you use tabs, you're not guaranteed that your code's going to look the same on one editor or computer as it will on another. So for the sake of cleanliness, don't use tabs. Now, we can argue about how many spaces you should use, whether it's 2, 4, 8. I mean, we can argue about that till the cows come home. Of course, 4 is the correct answer, but at least we can have that debate, and I'm open to it. But the tabs or spaces, I mean, there's just no debate there whatsoever. But essentially, that's kind of what we're talking about. That when it comes to code formatting, there's kind of a holy war that can be waged when it comes to should you put your curly braces after the function or should it be on a new line? There's a bunch of stuff. So I was playing around with Clang format, and I would say at this point, it's probably at like 97% to my liking. Because I have noticed there are like a couple of edge cases where it still does something where I'm not super keen on, where I kind of wish it wouldn't have done that. But one nice thing about Clang format is if you really don't like what it did, you can actually disable it inside the code by just doing a comment, doing Clang-format off and then Clang-format on when you want to re-enable it. So, but my goal was to try to limit as many of those as possible and just have the format do its thing. Because one thing and the other nice thing about this too is if I ever decide to change how I want to have my code styled, I can easily just update the Clang format, rerun it on everything, and everything's up to date. Because one thing I have noticed, as I was looking through all the various source files here, over the past 2 years of developing this, I've noticed my own personal coding style has changed a little bit. Like I've done things slightly differently. Specifically, one thing I've really tried to do recently is implement the column limit. So essentially what column limiting is you basically restrict how many characters your code goes in a single line. And the main reason why you'd want to do this in the first place is because this way it allows you to more easily put multiple, code windows side by side on the same screen without having to scroll left and right to actually see the whole thing of code. So that was one of the driving factors for it. But yeah, so basically just allowing me to just format everything, and in case I want to change something in the future, I can easily do that. Plus, it also, if it ever gets to the point where other people contribute to the project, it just kind of makes it look all uniform, because that, in essence, which I don't know if that'll ever happen, if anyone would ever contribute to it besides me, especially not while it's still in development, but in essence, that is why you would want to use Clang format, because if you're working on a super large code base like Google or Microsoft is, or the Linux kernel, having all the code look uniform makes it not only consistent, but it also makes it a lot easier to read. Because if you're trying to read through the code and it all looks the same, it's a lot easier, at least for me anyway, to comprehend versus, there's 20 different styles of, formatting going on. This case has the for loop, everything's condensed. This one, it's all spaced out. This if statement has the curly brace on the new line, but this one has it on the same line. This one is using tabs. This one is using 4 tabs or 4 spaces instead of 8 spaces. So it's a little harder on the eyes, if you will. But the reason, like I said, why it matters is, in essence, it really doesn't matter how you format your code. So even if you're wrong and you're using 2 spaces rather than 4, as long as you're consistently using 2 spaces rather than 4, we don't have an issue here. Similarly, if you're putting your curly braces on the same line rather than a new line, it doesn't matter as long as you're doing it consistently. So, at least in my humble opinion, it's less of a matter of how you format your code, but more of a matter of do you format it consistently, and Clang format definitely helps you do that. So that was quite a task I undertook. And the other 2 things I'll touch on just quickly here is I created what I called a sprite extractor. And basically what this allows me to do is take an entire sprite sheet with multiple different objects on it and essentially extract out the specific sprites I want and create objects from that while not having to load additional resources into the GPU, into memory. So usually when you try to load a sprite, for instance, you load the sprite and then you have the object either displayed on the screen, or it's a larger sprite and you only display part of it and you can kind of loop through it and do some kind of animation thing. So the initial thought I had of how to do this was essentially take the sprite sheet and then essentially carve out the individual sprites I wanted and then extract those and create it. Each object that the sprite extractor creates have its own sprite attached to it. But then I realized that's a basically a huge waste of memory because each one of those objects has to allocate a resource onto the GPU for that sprite. And in cases that I'll probably run into eventually, where I'm creating like larger scenes and there's going to be multiple reoccurrences of the same sprite, at that point you're essentially just loading the same sprite into memory multiple times, and it's kind of a waste. So the goal here was essentially to create a class that can take a single sprite or a sprite sheet, loaded that into memory, and then based off that create objects that reference the same sheet in order to try to preserve some GPU memory and whatnot. So that was the goal of it. So far, it's been working out pretty well with the Pokemon screen that I've been working on, which is, see how I did that segue right there? Pretty smooth, I know. So I worked on getting that implemented. So as far as the functionality goes, it's basically done. So like you can navigate through all the various different screens. I'm still working on populating it, so not all the data is populated in there, but I started to work on that, and that was essentially what I got up to this week. Not as much as I wanted to, but again, I was kind of going to war with Clang for a decent amount of this week, well, or at least time that would have been spent writing code. I was instead running the Clang format, seeing how it looked, reverting back, running it again, reverting back, changing some things, and, just going through the whole process. But what made it super easy was the fact that I had Git, because Git just allowed me to just reset the file back to what it was and wouldn't have to worry about any of that shenanigans. So it was definitely very awesome. Another reason why you should definitely be using source control for any project you work on. Now let's get into the main topic of the episode, which is comparing monolithic architectures versus microservices. So let's start off with the one that I'm sure everyone is familiar with, even if you don't know it by name, which is the monolithic architecture. Now, this one has honestly been around since the beginning of software development, and if you've ever written a program before, this is the architecture you unknowingly used, because monolithic architectures are just applications that are built single, everything's contained, it's one unit, all the components needed are directly compiled into it or linked to it through something like a shared library. So, like I said, they've been around since essentially the beginning of software development, and they're really useful for applications that don't require high scalability or distributed systems. So if you don't necessarily need to scale the program out, or if you're just writing a single desktop application or a command line program or a video game or something like that, generally monolithic is what you're going with. And as we'll get into scale, the microservices one is kind of more niche, I would say. But going into why you might want to use monolithic applications, some of their benefits is their simplicity, right? Like I mentioned, this is essentially the most simple app you can make, most simple program. Whenever you first start writing programs, you're writing monolithic programs. It's really easy to implement. It's really easy for you, the developer, and other developers to kind of understand how things work. You don't have to worry about all the overhead involved with managing dependencies of different services, networking together, APIs, or application programming interfaces, all that jazz. You don't have to worry about it. Everything is just right there in the source code, in the executable. And this kind of leads into potentially faster development and deployment. Again, it kind of depends on what you're making, but in the sense of everyone being up to speed on how to develop and deploy the program, it can be faster because you don't have to, like I said, you don't necessarily have to worry about how everything connects together and deploying individual things. You can basically just get up and go, write the code, and deploy it. It can, so you don't have to worry about the APIs involved. You don't have to worry about how the services network together. And if you have to make any changes, you can just work out of the same code base. You don't have to worry if you're writing the changes in the right code base or not. Everything's just in the same one. And this next point here is one that might be potentially underrated, which is reduced network latency. So one thing with microservices is generally first off, they have to be networked together, because in essence, as we'll kind of get into, microservices, you can basically think of them as separate programs or separate functions. If you think about them as separate functions, you can kind of imagine when you make a function call in your program, all that memory and handling of pushing things onto the stack and all that stuff is handled internally by the program. But if those functions aren't in the same program, you have to find a way to get the data from one function into the other, and the result, the reverse of that, getting the result out of that function back to the function that called it. So you have to do that somehow. Generally, if you're using a microservice architecture, you're doing that through some kind of networking, so there's network traffic going on, so you have the potential for network latency. Whereas if you build a monolithic application, everything's just happening locally on the same box, which in fairness, you theoretically could write a microservices architecture on the same system and do some kind of shared memory type solution where basically you allocate memory that you allow to be shared between different processes, and rather than having to network locally the different components together, you can basically just tell the other program, hey, go reach into this memory address here. That's where your variables are. Pull from them, do whatever you need to do, put them back there, and then I'll grab them and continue doing what I'm doing. So shared memory is a potential solution that you could do, but again, you kind of have to be working on the same system for that, because if you're not on the same system, of course, there's going to be some network traffic going on in order to transfer that memory around. So network latency is something you could potentially see, and you don't really have to worry about. Well, you could potentially see with microservices and wouldn't necessarily have to worry about with a monolithic program. Another thing is it can potentially be easier to test, because if you're writing test cases for the monolithic architecture, you can essentially just write a single suite of test cases that run against the program whenever you build it, and you can just check it. You don't necessarily have to worry about am I checking every use case of this specific microservice and all of the various spaghetti arms that it connects to throughout the program, because how this function how function A interacts with function B could be potentially different than how function A interacts with function C. And making sure that all of those microservices are up and running at the same time so you can perform those tests definitely adds a lot more complexity than you just build your singular binary, run your suite of test cases through it, and you're done. Similarly, because everything is just one application, you can potentially minimize your attack surface, because if you're not deploying a bunch of these different, microservices across tons of different machines, if you just have a singular application running on a singular machine, you don't have a bunch of systems that are potentially vulnerable if you have a vulnerability in your microservice. So if you had like a microservice to say process some kind of transactions, and there was a bug in there that could potentially allow an attacker to draw an account or something. If you have that microservice scaled across, hundreds or even thousands of servers, you now have that vulnerability scaled across hundreds or thousands of servers. Whereas if you're running a monolithic application, it would only be in one spot. and which I guess it could potentially be in multiple spots if you had multiple instances of it running and you were load balancing the application. But generally, you're not going to be as largely scaled with a monolithic application as you would with a microservices one. And speaking of microservices, we've kind of talked about them a little bit here, so let's get a little bit more into what they specifically are. So kind of as I touched at the top of the episode, it's what all the cool kids are doing with their Lambda functions in AWS. But essentially, what they are is they're designed to be small, independent services that communicate with each other through some kind of API or application programming interface. And each microservice is designed specifically to perform a single function within a larger system. So essentially, you could think of this as if you had some kind of web server or something. You would have a single microservice for handling the user authentication, and then you would have another microservice for handling the database, and then you might have another one for like handling the UI or something. And you basically split up each of the individual tasks into their own function or their own program essentially, and have them all communicate and work together. So one of the benefits of this is it allows for super easy continuous integration and delivery, so CI/CD. The nice thing about this is you don't have to change and recompile the whole program to push changes. If you only need to change how you're handling your user authentication, you can just make a change to that code base, make the push. It then does all of its CI/CD goodness, deploys that one singular microservice, and nothing happened with the rest of your program. Everything else is working as it's supposed to, and the only thing that changed is the user authentication. You didn't have to worry about running your full test suite against all of your other services because they didn't change at all. So it is definitely nice for that CI/CD goodness. Another thing that can be done is they can be developed and deployed, kind of as I mentioned, independently. And because they can be developed independently, this can allow for a couple of things. First, it can allow you to have more frequent releases because, like I said, if you only have to focus on a single small component, it allows you to quickly make updates to that single component and push those to the larger project without messing with anything else, like you would with a monolithic application. And the other thing you can also do is this: you could also do kind of A/B testing, if you will, where you could create a certain change, kind of push it out to some of your production servers, see how your users like it. And if they don't like it, then you can just roll back that change and push the old one. Whereas if you were doing this with a monolithic application, you would essentially have to create different binaries for each version that you want to test out on people and deploy those to various servers and direct the traffic accordingly. Whereas the microservices, you can basically program the change, deploy it to a select few servers, see how people like it. If they like it, you can deploy it to more servers, and you can have more. It's more dynamic in how you can deploy that stuff. So coming into some of the specifically, I guess, best practices or kind of the pros of microservices, they're very small, and it's best to keep them small, and theoretically they should only perform a single function. So this is kind of where the Lambda functionality comes into with AWS, where rather than a monolithic application where you might have multiple functions, multiple classes, multiple objects all kind of joined into one, each microservice essentially only performs a singular action. So like we talked about user authentication, that's a singular action, and that would be a potential use for a single function or a microservice. Another thing that is generally used with microservices and best practice also is containerization. So essentially running your microservice within like a Docker container or something like that. There's a couple benefits to this. One, as we've talked about before with Docker, is all of the dependencies that are required for that application to run are contained within that Docker container, so you don't have to worry about is the underlying system I'm running this on compatible, or does it have the necessary dependencies? All of them are included directly in the Docker container. The other nice thing about using Docker containers is you can use Kubernetes, which essentially has its own kind of, scalability feature where if you're hit with a bunch of traffic at once, you can dynamically scale up, how many of these containers you spin up, and then you can also dynamically spin them down as your needs decrease and your traffic decreases. So that's another benefit to doing microservices with containerization. It adds to the scalability factor as well. Also, if you're just doing singular functions rather than like small programs, that can be what allows you to use things like Lambda functions in AWS, which Lambda functions are similar in the sense that they only run when they're called upon, and they can also dynamically scale as the load increases as well. So that is one of the draws to Lambda functions, is how scalable they are, and essentially you only pay for the minutes you use. So if your specific microservice isn't doing anything, you essentially don't get charged, and you're only getting charged for when you're running and when you're executing, and of course as you scale as well. Another thing is implementing a service registry. So service registries are essentially used to keep track of all the available microservices and their locations, which makes it a lot easier for all the various microservices to communicate with one another and to enable that dynamic scaling feature. So if you're, say, if your specific microservice is trying to communicate with another one, if it doesn't know where it is and has to kind of figure it out on its own, that's definitely going to induce some latency and some slowdown in your overall program's application speed. But if you have a registry where these services can just do kind of basically a lookup of, where's the service I need to go to. Like if you're networking these together, what's the IP address, what's the port number, that kind of a thing. It can definitely increase the speed of how the things communicate together. Another one is, we've talked about this before, the API for communication. So generally with microservices, they use some kind of API or application programming interface to enable that communication between the various microservices, which allow them to interact with a standardized way. Because one thing when you're dealing with any kind of networked programs, you have to come up with some kind of protocol for how they interact with each other. So if you're creating a microservice architecture, that's kind of where the API comes into place, because if you have a dedicated API for how these different microservices are supposed to interact with each other, it definitely simplifies the programming process, because you don't have to reinvent the wheel every single time you're trying to write a new microservice. You can essentially just make a call to the API that will handle all of that, communication stuff for you to basically streamline the development process. Another one is implementing circuit breaking. So essentially, if you have a microservice that goes down for whatever reason, whether it crashed or you took it down for maintenance while you're uploading the new version, the point of circuit breaking is to essentially prevent a cascading of failures. So if one service... So, for instance, if your logon manager interface detects that the authentication service is down, it's not going to, then try to go to the navigation or authentication service, get some bogus back because it wasn't able to authenticate, and then try to go to the database to try to do some request with the bogus data, causing another crash there. So essentially the point of the circuit breaking is for the individual microservices to be able to detect failures in order to prevent future failures and cascading failures, which would definitely improve the resiliency and the reliability of your program. And again, kind of as we touched on, just the overall, the CI/CD capabilities of microservices, being able to only push the changes of the specific service you want, only having to modify that section of the code, and you can just quickly and easily push that change and automatically gets deployed, is definitely beneficial. So we've kind of talked about microservices in this kind of abstract, theory, like, yeah, it's cool and you can like network these things together, but what are some actual use cases? Because like we talked with monolithic applications, it's your things like your desktop apps, your games, just your kind of standalone things. But what the heck are microservices? What actually uses these things? And it's generally more tiered toward like anything kind of web or internet based. It's not something specifically that you're going to be running on your local machine, for instance. Now, you definitely can, but, like as we kind of mentioned with microservices, the appeal and the allure to them is their scalability aspect. And I kind of doubt you would generate enough traffic by just you alone on your personal machine in order to warrant the scalability factor, because again, it's just your machine and the resources on your machine are limited. So you'd definitely be better off with a monolithic application, because you could easily just allow the monolithic application to have access to all the resources on your machine in order to do the scaling, because that's basically what the microservices architecture would be doing anyway. So the point of them is to be able to be distributed across multiple machines, multiple servers, across multiple data centers, and be able to scale dynamically. So one of the big uses for microservices is the financial sector, because one of the reasons why it's important is for things like banks and other payment processing companies, is having a microservice to essentially being able to handle the specific functions of those transactions. It not only improves the speed, because you don't have to go through the entire monolithic application of handling, checking what kind of thing I'm doing, sending it off to whatever process it needs to go to, getting the response back, returning it to the user. For instance, if I'm just processing a transaction, that can go directly to that microservice, process the transaction, and boom, you're done. Similarly, you can do it for user authentication, fraud detection, regulatory compliance. You can really split up all the different components of handling various things in the financial sector with microservices. And that's, of course, really vital, because the last thing you want is to be, out, at Walmart or something, trying to pick up your chicky nuggies, and you're waiting for your credit card to go through, and you're just sitting there while your frozen nuggies are starting to defrost because your transaction's taking too long, and then next thing you know, your nuggies are bad because they've completely defrosted, and now you just have soggy, wet, gross, disgusting nuggies that you can no longer eat. So of course that was a very unrealistic situation that you'd probably encounter, but the point being is, we kind of take for granted these days, if I go up to, the gas pump or the cashier or wherever and, insert my credit card, that transaction is done pretty quickly. So we kind of take for granted the fact that this is done so quickly, and part of that is due to these microservices and that ability to just scale dynamically. As more people are making transactions, you can scale your services up, scale multiple instances of those functions up if you're using Lambda functions, or add more Docker containers through Kubernetes, or whatever the case is, you can dynamically scale to accommodate that load. And then another one that is also used is just kind of web servers in general. So pretty much any one of the big social media companies or streaming services, definitely going to be using microservices there. Other things like e-commerce platforms as well could also benefit from microservices. So you could essentially have a different service for handling the user authentication, kind of as we touched on, the content delivery, handling the search functionality. That could be another microservice for handling the payment processing. And essentially just breaking down, the large application of your website into the individual pieces in order to improve that scalability and reduce the overall development time, since you can just focus on those individual pieces and deploying the new features. So we kind of talked about both the monolithic applications and the microservices. So let's kind of try to compare the two and see which one could potentially be better for your use case. So starting off with why microservices are better. First is the flexibility and scalability. Obviously, monolithic architectures are a lot less flexible and harder to scale than microservices because the entire application is built into a single thing. It's a single executable. It's not, multiple functions or multiple executables that can essentially run independently that you can scale dynamically. So it can be potentially challenging to add new features or functionality without potentially significant code changes to the code base, because you potentially might have to do a lot of refactoring, or if you touched a core component of the code, you then have to retest against everything that uses that code to ensure you didn't break something. So there can potentially be some scalability and flexibility issues when dealing with monolithic applications. Another issue with monolithic applications compared to the microservices is they are less fault tolerant. So because that entire application is a singular application, if something goes wrong or something fails or a array goes out of bounds or you reach some kind of exception or something happens, that can basically take down the entire program. Whereas on the microservices side, if you have, something take out a function or you encounter some kind of exception, only that one service would go down and the rest of the application would still be up and running. So that is definitely a drawback to the monolithic application, where if you encounter some kind of error or issue, the whole thing could just crash on you. Whereas a microservice, you could maybe have a singular component crash, but the entire application itself wouldn't. Another potential drawback of the monolith is the limited ability to deploy independently. So generally, you can deploy. It's because everything's kind of bundled together, right? You have this singular executable. It's either all ready to go or it's not ready to go, right? If the program doesn't compile, the program isn't shipping. If a single portion of the application hasn't been updated to what it was supposed to be for the feature release, you're on hold until that feature can be implemented. Whereas the microservices, once something's ready to go and tested, you can just immediately deploy it. You don't have to wait for, John Doe over here to get his butt moving and implement his feature. Whenever he does it in the microservices world, he can just push that and everything else is already up and going, ready to go. So that is one potential limitation of the monolith, is because everything is built into a single application, you have to wait until everything is ready before you can then push and deploy that new version of your changes. So, and this kind of ties into the next thing I wanted to touch on, which is increased complexity, in the sense that as far as the operations is concerned, so if you think of the DevOps mindset, there's more complexity in kind of making sure, are all of the components that we were trying to update for this new version, are they all updated? Is everything ready to go? Does everything pass all of our test cases? Whereas for microservices, because everything is a lot smaller and can be deployed individually, from the operations perspective, you can just check, is that portion ready to go? All right, cool, ship it. Is that one ready to go? Cool, ship it. And you don't necessarily have to wait until everything is ready. And it kind of also doesn't hold up the development process, because you can just kind of continue, working on, your portion of the features with your specific microservice. Now, you could potentially do something similar in the monolith if you had, multiple branches. You could merge your changes for the new release into like the master branch, for instance, and then go off on a development branch and start implementing some additional features. But then you have to, worry about merges and pull requests and all that fun stuff. Whereas if you're doing the microservices, you're essentially working on your own portion of the code, your own application, your own, potentially even your own Git repo that you can just work out of, and you're not necessarily waiting on others to do their stuff before you can then, move on with your development. So that is some of the pros of microservices over monoliths, but that's not to say that monoliths don't have their wins as well. And one of the key wins that I think monoliths have is their simplicity. Because as we kind of said at the beginning when we started talking about these two things, monoliths is what your go-to is. It's what you first learn to develop for. It's stupidly simple. It's just a single application. You don't have to worry about things that are networking together. You don't have to worry about writing an API. You don't have to worry about any of this complexity. Everything is just inside the code base you're working in, and it is very simple. And speaking of simplicity, it's better depending on your use case. If you have a specific use case for an application, monoliths are probably just the best way to go, just because if you have a specific use case, it kind of defeats the purpose of the microservices, because the microservices are essentially to break down a larger problem into individual use cases. But if you only have a specific use case, that's basically the point of, a singular microservice. But if that's the only point of your project, then there's no point in doing microservices. So that is one benefit the monoliths have, is if you have defined requirements and scalability isn't necessarily a concern or an issue, it's honestly a lot easier just to create a monolithic application. So, kind of some examples of this is if you have like a small to medium-sized website where you don't necessarily have to worry about massive scaling concerns, or if you're creating any kind of like desktop application that's just going to run on a single computer. Things like this where, the need to scale out and dynamically allocate resources is more limited, and everything's kind of contained and has a specific use case. That would be, kind of a prime example of where a monolith is definitely the way to go. And this next one here is it can kind of go both ways in terms of resource utilization. So on the one hand, you could make the argument that microservices would be more efficient when it comes to resource utilization, because if it's only performing a singular task, that could potentially be less less resource intensive than, say this massive application that's, taking up multiple megabytes or potentially even gigabytes of RAM and occupying multiple CPU cores while it's running its, monolithic application, whereas the microservice is, only housing a few megabytes and, only impacting the CPU when it gets called upon. But that could be true. But the reason why monoliths could also be less resource intensive is because if you're running just a singular application, generally speaking, scalability isn't the goal here. So you don't need, tons of servers distributed across multiple data centers with the ability to scale up and scale down, which could potentially add, more resources. And just in general, your infrastructure costs would be reduced if you're only, having to deploy, a couple instances of your monolith application, if you're even deploying them, or if it's just, like a desktop application, you don't even have to worry about it. But the overall hardware and infrastructure cost is definitely higher with microservices, because generally with microservices, you're targeting that scalability aspect, and in order to scale efficiently, you need, lots of infrastructure resources to be able to accommodate all the load that you could potentially generate, which is why monoliths can be actually less resource intensive, which in some ways could, is kind of even counterintuitive. But at the end of the day, when it comes to should you go with the microservices route or should you go with the monolith route, it generally just kind of depends on what type of application you're trying to build. Because if you're trying to build something that needs to be highly scalable and the ability to be distributed across either multiple servers or even multiple data centers across the world, microservices is definitely the way to go. If you need that, high availability, high reliability, fast response times to user input, that's kind of where the microservices architecture shines. But if you're just building a single standalone application for maybe it's just your personal website, or you're just making a desktop application or command line program, that's where the monolith is honestly the way to go, because it would just make your life a lot easier. Now, that's not to say you couldn't make a personal website based on a microservices architecture because you want to learn how microservices work, because that is 100% a viable use case. And honestly, any type of application, even if it's a single-use desktop application, in theory, you could absolutely create it into a microservices application just because you wanted to, because let's be real here, that is kind of the point of personal projects. Is it's not always, can I make the most efficient, most optimized, best program in the world, and more so about how can I learn from this? What kind of learning experience can I get out of this? That's one of the reasons why we have home labs. It's so maybe it's because we want to run, enterprise hardware and run certain applications that we enjoy. That is definitely a component to it, but also, at the core of home lab, the lab specifically is in order to be able to test things out, have a sandbox environment where you can play with things, learn new technologies. And if one of those things for your software development career is to write a totally overkill microservice architecture to, house a simple website for yourself, absolutely knock yourself out. But that's basically, what it comes down to, though, is when it comes to a production scenario, like in a corporate world, it really comes down to what your application needs to do. If you need scalability and the ability to be distributed, microservices. Otherwise, probably just go monolith, because it makes things, generally speaking, a lot easier for your developers. So that is the kind of the comparison between which one, monolith versus microservices. Hopefully you learned something in this episode if you hadn't heard of one before, or maybe you had heard of them before but not the name, or you only heard of the name, whatever the case may be. Hopefully you learned something. But before we go, let's get back to our trivia question. And this week's trivia question is the CUDA API, which is the way that you write code in order to run on an NVIDIA GPU, was released in what year? And if you said 2007, you are correct, and you got this week's trivia question correct, so congratulations if you did. And if you enjoyed the episode, definitely be sure to leave it a rating and review. Subscribe if you haven't done so already. Share it around. And if you have any questions about this episode, or if you have topics or comments for future episodes, definitely shoot me an email at contact@darkassassins.inc.com. That is down in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.